and the milliamperage is 2100 milliamps. So I take 2100 plus 2100 plus 2100, that gives me a pack with 6300 milliamps or 6.3 amps. It's exactly the same terminology. This pack is referred to as a 3S, 3 in series, and 3 in parallel. So with the small helicopters that we're talking about, they're simply powered by simple 3-cell packs, 2-cell packs, and so you won't really see this terminology too much. But when you start to get into larger electric helicopters, you'll see this terminology, and now you know how it works. Now let's go ahead and take a look at various types of chargers. Here are 4 different types of chargers, and they literally range from small and simple to larger and more complex. Let's start from small and work to large. First, of course, here's the E-flite charger that we looked at. It is a 3-cell charger, and the output is 800 milliamps or 0.8 of an amp. It's specifically designed for the little 3-cell pack in the Blade CP Pro. Next, we have a selector charger. Now you have to be a little careful as you use this charger because it has switches to set the cell count and a switch to set the amperage. The amperage goes from 250 milliamps to 2 amps. So this charger is capable of charging the 11.1 volt 2100 milliamp pack that we'll use in the T-Rex. After that, we've got the Triton Junior by Electrofly. It's a little bit more capable. It can handle 4 cells and the maximum charge rate is 5 amps. After that, we've got the Astro 109. It can handle up to 9 cells and the maximum amperage is 8 amps. This charger is neat because all that you do is you turn down the amperage adjust, you plug in the battery pack, it automatically reads the cell count, you just verify the cell count, then you increase the amperage to what you want, anywhere from a trickle charge to 1C, and then it's hands off. It does all the rest. In terms of powering these chargers, we have 2 options, either a large 12-volt battery or personally, my favorite, the Astro Power Supply. The Astro Power Supply is great because it fits into my T-Rex travel case. In terms of the small E-flite charger, we have a little wall wart charger. Now, one Astroflight item that I just can't be without is my little Blinky balancer. Let's take a closer look at what this balancer does. The bottom pin on the Blinky is negative, and all of the other pins are positive pins for the number of cells in the pack. So 1-cell pack, 2-cell pack, all the way up. The LEDs for a single cell pack, 2 LEDs for a dual cell pack, 3 LEDs for a 3-cell pack, and on. Now let's go ahead and plug in a battery. What the Blinky does is for the first 5 seconds, it checks to see if all the cells are above 3.2 volts. And so if the LEDs light up, that means that all of the cells are above 3.2 volts. There's the 5-second check. The volts are good, and now the Blinky will start to bring down the high cells indicated by the LED until the pack is balanced. This pack is pretty far out of balance, judging by the way it's blinking. As the packs get closer to balancing, the lights will blink slower. Here's another pack. The 5-second check, all the cells are good. And this pack is basically balanced. And the Blinky just sits there checking the voltage of each cell, and when it sees a little disparity, it'll come on. Again, this pack is really good. Finally, for the third pack, there's the voltage check, and it looks like, okay, I was going to say 1 cell, looks like 2 cells are a little high. Again, when the lights blink at random, that means the pack is very close to being balanced. So the Blinky is a cool little tool that I just couldn't live without when I fly my electric helicopters. You may be asking, why do I need the Blinky to keep the cells balanced in a LiPo pack? Because the LiPo packs are very touchy. They're touchy to temperature. They're very sensitive to overcharging. They're very sensitive to undercharging. And so the main purpose of the balancer is to keep the cells within the pack balanced, so when you charge the pack, you don't damage the pack. For instance, if this cell is high and these two cells are low, the high cell is going to be damaged when the charger tries to sense the cutoff voltage. And that's why the Blinky is so important. Now, if you charge the cells with the wrong settings, they can catch fire. So you always want to charge LiPo packs inside a fireproof container, and make sure somebody is at least in the room, so if a fire starts, that somebody's there to catch it. Otherwise, you can burn down your shop. I'm going to go ahead and start to charge this with the Astro 109 charger. First, I want to make sure that the voltage is all the way down, and then I can go ahead and hook up the power source. And then the Astro charger is going to say, waiting for battery. When I plug in the battery, now it's sensing three cells, and it's a three-stage charger. It's on stage 1. Here's the time, and then for the amperage in the top corner, I'll go ahead and adjust the amperage up to 2.1 amps. There's 2.15. There's 2.1 amps. If perchance this battery would have cells below 3.2 volts, I would simply dial down the charge amperage to 200 milliamps, which would be 0.2 amps. So right there's 0.2 amps. I'd keep the pack on the charger for 5 or 10 minutes. Then I would check the voltage with the Blinky, and then I could pull the charge current back up to 2.1 amps. Now the other thing is that during the charging, you can plug the Blinky in, and the Blinky will automatically balance the pack during charging. So that's pretty cool. I've got everything set up. I'll put the pack in the crock pot, and we're all set. With the soldering chores done, what do you say we build a T-Rex 450? Now, I'm not going to give you a blow-by-blow description because I've done that in volumes 4 and 5 of my authoritative DVD series. But I am going to highlight some of the things that you really need to know as you build a T-Rex 450. Before you assemble the top of the side frames to the bottom of the side frames, we need to do some preparation on the edges of the side frames. We do this so that no matter how the radio is installed, the sharp edges of the graphite or the carbon fiber won't chafe the wires. So first of all, you can either do it all with a small piece of 320 sandpaper and sand the outside edge and then sand the inside edge, or you can use a little drum sander and in a Mata tool just brush the outside edge and then brush the inside edge, and then go ahead and just touch it up quickly with a little piece of 320 sandpaper. The areas on the lower side frames that you want to do are this trough area, the front from here down to here, and then the bottom from the front skid all the way back to the back skid. After you have everything sanded, take a Q-tip and pull most of the fuzz off of the Q-tip. Then soak the Q-tip with thin CA, and then just run the Q-tip along the edges, and the thin CA will seal the edges beautifully. For the top portion of the side frames, sand and CA from here down along the front and up around the bottom until you come to this point. In order to get the Hi-Tech 65 series servos to fit in the servo mounting holes, you need to modify the holes just slightly. You can do that with either a Dremel carbide bit or with a small rat-tailed file. And what you want to do, well, first of all, the top hole is stock. Notice how it's rounded in the corners. And then you want to take either the file or the bit and essentially pull out the corners just a little bit. Then also you'll need to elongate the rear mounting hole out just a touch and the forward mounting hole out just a touch. Here's a hot tip to mount the speed controller to the side frames. Buy an extra battery plate. Then drill a hole in the top right corner of the battery plate, 1 millimeter from the top and 1 millimeter from the front. Then take the plate and place it inside the side frames and take a long screw and place it through the pre-drilled hole and slide it through the hole that you just drilled on the battery plate. Then put a block of wood behind the plate, hold the plate level, and then use this pre-drilled hole to drill through the battery plate. Once that's done, go ahead and assemble the battery plate to the outside portion of the side frames. When you mount the struts to the side frames, the holes in the struts really don't line up with the holes in the side frames. To rectify that, drill each hole with a 96,000th drill bit, and that will enlarge the holes and let these screws line up much better. One of my skids was nice and tight in the strut, and the other skid was almost sloppy loose. So if you have a skid that's too loose in the strut, simply drill a little hole in the strut, align the skid the way you want, and then put a drop of thin CA in the hole. You'll have to circumcise your ESC speed controller. Here's the stock unit, and notice how the heat shrink tubing covers a lot of the cooling fins. So what you want to do is basically cut it away on the edges, and you'll end up with a piece that looks like this. This ensures that your ESC will stay as cool as possible. Here's the carbon battery plate mounted to the right side of the helicopter. Again, if you wanted to, you could mount it to the left side of the helicopter. Anyway, when it's in place, just make sure that there's clearance between the bottom of the main gear and the top of the plate. You may want to grind or sand away 1 millimeter in this top left corner. Then put on double sticky tape to mount the ESC. I like to use ACE tape as it peels off easily and doesn't leave any residue. And make the pieces about 3/4 of the way down the battery mounting plate, and then go ahead and stick the ESC down, and the front of the capacitors should come flush with the front of the plate. Here's the ESC in place with a zip tie for added security, and all the wires are connected to the motor. To auto-rotate the T-Rex 450, I'm going to change the tail rotor from a driven tail rotor to a non-driven tail rotor. With a non-driven tail rotor, there's much more inertia in the main rotor system because the main rotor doesn't have to drive the tail rotor. To do that, we're going to use some small pieces of 1/32 plywood, and you take those pieces and just put them in between the top gear and the bottom gear. You can see how I've got one in position right here and also one up here. After they're in position, go ahead and drill 2 holes through the bottom ribs all the way down through the top ribs as well. Feed 20 thousandths safety wire, which is available at your local airport through your A&P mechanic. He should have some. Go ahead and twist it, fold it over, and then when that's done, cut the ribs here, here, and here so that this whole inner part of the main gear will pull free. After you've done that, go ahead and rebalance the main gear on the high point and just shave away plastic here and here, again, wherever the plastic needs to be shaved away to balance the main gear. With that done, you'll have a non-driven tail rotor and you'll be all set for auto rotations. Here's the bottom of the main gear after I've sliced through all the ribs. I will have to press out the steel collar from this residual piece of plastic, and here I can go ahead and pull that piece of plastic out. There's what we're left with. Now the bottom of the main gear is one integral piece with the top main gear, and we've got a non-driven tail rotor. I think it would be nice if Align came out with an optional gear designed like this so you wouldn't have to do the modification yourself. Here's the steel collar slipped back into place in the Sprague bearing. When I auto-rotate the T-Rex with a non-driven tail rotor, I have to rely on the vertical fin to weather vane and hold the nose straight. To do that, I want to cover up the holes in the vertical fin. Callie from Callie Graphics has designed these stickers that cover up the holes both on the vertical fin and on the horizontal fin. On the horizontal fin, when it's covered up, it gives better pitch stability when the ship is in an auto rotation. There are two things I want to point out to you with regard to the motor that comes with the T-Rex. When you install the pinion, keep it 1 millimeter down from the end of the shaft. Then the other thing, I've heard reports that when the motor gets hot, sometimes the bottom of the case will fall out, with disastrous results, of course. To prevent that, I just use 2 little zip ties and zip tie the bottom of the motor to the outside can. Here's the stock main gear in the T-Rex 450S. Align has recently come out with a beefed up main gear. You can certainly see the difference in the construction. I prefer the original main gear simply because it's lighter than this piece, but the advantage of this piece is that with 4 screws you can remove the Sprague unit if you mess up the main gear. So it's much easier to put on a new main gear. With the old main gear, you'd have to press the Sprague in and out of the aluminum housing, and so I still prefer to do that because of the lightness, but some of you may want to go ahead and buy the optional main gear. When you mount the motor, you just want to push the pinion all the way against the main gear so there's no play, and then rotate the main gear and feel for the tightest spot. Once you find the tightest spot, make a mark, and here's my little mark on the main gear that indicates that. Then I want to change shots, and I want to give you a feel for the type of play that you're looking for when you set this mesh. Basically, you want very, very little play at the tightest spot, and then all of the other spots will have slightly more play. Now I want to give you a visual look at what the gear mesh should look like, but I also want to give you an audio feel for what the gear mesh should sound like. Here the gear mesh is set at the tightest spot, and so just listen and look. Now if I rotate the main gear 90 degrees, we'll have more play. Again, listen and look. And that's what the proper gear mesh should look like and sound like. I had a friend email me the other day, and he said, "Ray, I broke my tail rotor bell crank. What's going on?" Well, this is what's happening, and this is why he broke his tail rotor bell crank. When I was first assembling my T-Rex 450S, I was sliding the slider back and forth on the tail rotor shaft, and I slid it to one extreme, and I came back, and it just locked in place. It's like, whoa, this is a problem that needs to be fixed. So I did 3 things to rectify the problem, and here are those 3 things. First of all, the shaft on the 450S is black anodized, and I think that anodization may be a little soft or a little bumpy, and so I took some 600 paper and just polished the tail rotor shaft to make it as smooth as possible. Then here's the little brass insert, and it's beveled on each end here, and the edge of the bevel is very sharp. It's a very sharp corner, And so again, I think that it's catching because there's a little bit of play in this slider and the edge can catch on the shaft. So you can do two things. Take a small rat-tailed file and bevel off the edge, or take a piece of 320 sandpaper, roll it in a conical shape, and then insert that into the slider and just twirl it to sand off the sharp edge on both ends. Finally, add 1 drop of lightweight 3-in-1 type oil to the tail rotor shaft so that the slider can slide on the oil. Normally, I don't like to add oil to the tail rotor shaft because we want the slider to be able to move very quickly to respond to the gyro inputs. But in this particular case, I want to make sure that the slider doesn't hang up on the shaft, so I make the compromise with a drop of oil. If you do these 3 things, I can guarantee you that you won't break a tail rotor bell crank. Notice how I've enlarged the hole in the tail rotor gearbox right around the tail rotor shaft. I do this for 2 reasons. First, it allows the brass slider to slide in and up against the bearing, which gives more right tail rotor authority. The other reason I do it is to get perfect spacing of the bearings around the tail rotor pulley. Let me go ahead and change shots and I'll show you what that looks like. In the plastic tail rotor gearbox, if this bearing is fully seated to the left and if this bearing is fully seated to the right, you can have play in the tail rotor shaft, and I think you can see that. 2 of the T-Rexes that I built did not have this play. The 3rd T-Rex did. So the solution is to take a brass tube, slide it on the tail rotor shaft, and then push this bearing up against the tail rotor pulley. That will take all the slop out of the tail rotor pulley, and then the tail rotor shaft won't move, and that ensures that you have perfectly precise tail rotor pitch control. Here you can see the tail rotor pitch that you'll get in the stock form, where the brass slider just bumps up against the tail rotor gearbox. With that enlarged hole, now the